In this chapter, I used the Solow model to analyze the effects of automation by the use of industrial robots. And the source on which this chapter is based is the book by David Bloom and me, Automation and its Macroeconomic Consequences, Theory, Evidence and Social Impacts, in particular chapter 4. The starting point for this chapter are the following three observations. As you recall, the Solow model predicts that the labor income share is always constant, which was in line with empirical evidence until the 1980s, but it's not in line with empirical evidence since the 1980s, when the labor income share has decreased. Second, the Solow model predicts that long-run economic growth cannot be achieved by only accumulating capital. You need technological progress in the background. And third, the Solow model is silent on inequality because there is only one representative household, basically on the household side of the economy. So inequality cannot be analyzed in the basic version of the Solow model. The aim of this chapter is now to modify the Solow model to account for automation in terms of the use of industrial robots and to analyze how these predictions change. And what we will see is that this model can then explain a decreasing labor income share since the 1980s. We will also show that long-run economic growth becomes possible even without technological progress because the diminishing marginal productivity of physical capital is overcome by having a second production factor that obtains the role of labor but is physical capital in essence. And third, I will extend the model later on to allow for two skill types, high-skilled and low-skilled workers, and will show that automation has the implication in this framework that it can explain an increase in the skill premium. The importance of automation is emphasized by this graph that plots the worldwide stock of operative industrial robots in million units from the 1970s towards 2023. And we see here that throughout the 1970s and the beginning 1980s, the global stock of industrial robots was negligible. Then growth increased and we had an increase in the stock throughout the 1980s and 1990s to about 1 million industrial robots in 2010. And since then, the number of industrial robots really increased tremendously to 3.5 million units today. So the graph makes clear that automation is a rather new phenomenon. So this full substitution of labor that we have with industrial robots is basically taking place since the 1980s. And of course, we can imagine that this changes something in the model. And what we want to do in this chapter is to analyze to which extent it impacts on the central predictions of the Solow model. And we will see that there is a strong effect. And we start the analysis with the first implication of the Solow model, namely that the labor income share stays constant and by implication also the capital income share stays constant. For this, consider again the Cobb-Douglas production function of the standard Solow model without technological progress here, where output is produced with physical capital with an output elasticity of alpha and with labor with an output elasticity 1 minus alpha. Capital is typically assumed to be all the machines, production halls and assembly lines and so on, but there is a certain complementarity with labor. So you need workers to operate the assembly lines, you need workers to staff the machines and so on and so forth. So one cannot produce without the other. That's the central feature here of the Cobb-Douglas production function. If you let one of them be equal to 0, then also output would be equal to 0. Now we know in the standard Solow model there is perfect competition in this sense, so the marginal product of capital would be equal to the capital rental rate and the marginal product of labor would be equal to the wage rate. So we can just compute them. The marginal product of capital is the derivative of the production function with respect to the production factor capital. And that's equal to the capital rental rate, which is in turn the interest rate plus the rate of depreciation. And if we take this derivative, we see alpha comes down from the exponent of capital. We have k, the exponent is reduced by -1, and L to the power of 1 minus alpha stays here. So we have decreasing marginal product because alpha is between 0 and 1. So the exponent of k is negative, so k would be in the denominator, and as k increases, the marginal product therefore decreases. The marginal product of labor, which is then the wage rate in equilibrium, is the derivative of the production function with respect to labor, L, which is 1 minus alpha times k to the power of alpha times L to the power of minus alpha, because this exponent is also reduced by minus 1. Next, we use the wage rate and the capital rental rate that we've derived on the previous slide to compute total capital income and total labor income in the economy. Capital income is the capital rental rate multiplied by the total stock of capital. And if we divide it by GDP, then the result is the share of total income that is earned by the production factor capital. We see here, if we plug in the capital rental rate and multiply it by k, the result here is k to the power of alpha times L to the power of 1 minus alpha, and that's the same as GDP. So it drops out here, and what remains is just alpha. So the capital income share would be constant and equal to the elasticity of output with respect to capital. With the labor income share, we multiply the wage rate by the number of workers, so that's the total wage bill in the economy. And again, if we divide it by GDP, we get the share of total income that is earned by all the workers in an economy. We plug in what we've derived on the previous slide for the wage rate, multiply it by L, and again we see then that this expression here multiplied by L is again equal to GDP, because L to the power of minus alpha times L is L to the power of 1 minus alpha. So this drops out, and what remains is 1 minus alpha. Again, this is constant, and that's the elasticity of output with respect to the production factor labor. So capital and labor income shares are constant according to the standard model and equal to the corresponding output elasticities. And indeed, in the US, it has been constant for quite a long time until the 1980s, where the capital income share was about 1/3 and the labor income share about 2/3. Since the 1980s, however, as I said, the labor income share has fallen and correspondingly the capital income share has increased. Now we note from the picture that we've seen on the worldwide stock of operative industrial robots that also the number of robots has started to increase strongly in the 1980s, and it was negligible before. So the question looms whether the fall in the labor income share can be explained by the use of industrial robots. And intuitively, one could come up with the following narrative. So robots are actually a substitute for labor. For example, think about an assembly line, which is one form of physical capital, and industrial robots as another form of physical capital. You can see assembly lines that are staffed by industrial robots without any human workers there. So the workers have been substituted away by the robots. At the same time, the robots constitute physical capital and they are owned by somebody. And the income that the robots generate are channeled towards the owners of the robot. So therefore, in the production process, the robot substitutes for workers and thereby reduces the labor income share. But on the distribution side, it channels the income towards the capital owners, and therefore it could increase the capital income share. And what I will do now is to modify the Solow model so that it accounts for a substitute for labor and will show whether this is a plausible explanation. So for this purpose, consider a production function that is given here by this production function, which is again a Cobb-Douglas production function, but now it has two different types of capital, namely traditional physical capital, as I call it, and automation capital in the form of the industrial robots. And automation capital is a perfect substitute here for labor, so that's the extreme assumption if we take automation literally according to a dictionary that says it's the full substitution of labor by robots. Apart from this additional production factor, everything stays as it was in the standard Solow model. The output elasticity of labor is 1 minus alpha, and the output elasticity of capital, of traditional physical capital, is alpha. Now we can compute again the factor rewards, but now we have three of them. We have the wage rate as the marginal product of labor. So if we take the derivative of this production function with respect to L, what we get is 1 minus alpha comes down from the exponent here. The exponent is reduced by minus 1. So we have k over lp to the power of alpha, and we see that the wage rate decreases not only in the number of workers, but also in the number of robots employed in equilibrium. And by contrast, the wage rate increases in the amount of traditional physical capital employed. Then there is the rate of return on traditional physical capital. That's again the interest rate plus the rate of depreciation. That's then the derivative of the production function with respect to k. So for this, alpha comes down from the exponent, and k is, the exponent is reduced by minus 1 again. And what we get if we reformulate it is L plus P divided by k to the power of 1 minus alpha. So for the capital rental rate, it's exactly the opposite. So the capital rental rate would decrease with the use of traditional physical capital, but increase with the use of labor or robots, which is the second capital stock that we have. And then we have the rate of return on automation capital, which is, if we compute this, the same as the wage rate because they are perfect substitutes. So again, for the rate of return on automation capital, we get that it increases with traditional physical capital and decreases with labor or with automation. So the central point is wages are increasing in traditional physical capital, that's standard knowledge, but they are decreasing with automation capital, which is now the new element that we get here. Now we can use the wage rate that we've derived on the previous slide to compute the wage bill in the economy. So that's the wage rate from the previous slide, so this expression here, multiplied by the number of workers. And if we divide this expression by GDP, we again get the labor income share. So we rewrite this here, we take L plus P to the power of minus alpha so that it is in the numerator, multiplied by L, and we divide by GDP, which includes automation here. What we see is now that not everything cancels out as it was the case without automation capital. Only the traditional physical capital stock cancels out. But here L plus P to the power of minus alpha and L plus P to the power of 1 minus alpha in the denominator, they actually become L plus P in the denominator to the power of 1. And we have this L here. And we see the labor income share now in the Automation-Augmented Solow model is not constant. It's 1 minus alpha times L divided by L plus P. Now, if we compare this to the standard Solow model, where it was always constant, 1 minus alpha, we see here that the accumulation of automation capital, so an increase in P, actually reduces the labor income share. And by symmetry, the capital income share would increase with automation. Now we put the things together. Until the 1980s, the number of industrial robots was negligible, so close to zero, and therefore the labor income share would be given by this expression for P equal to 0, and then we see L divided by L cancels out, so it would be constant and equal to 1 minus alpha. So until the 1980s, the standard Solow model explains the labor income share quite well. Since the 1980s, we now have that P increases. And then since the 1980s, therefore, we have a decrease in the labor income share. So we see that in principle, an automation-augmented Solow model can explain why the labor income share decreased since the 1980s. But of course, in reality, the mechanisms are more complex, and in particular, there are also additional factors at play. So automation is not the only factor in the decrease in the labor income share. However, automation plays certainly a role, and this seems to be established also empirically as the literature has shown. Now we move on to another central prediction of the Solow model, namely that you need technological progress for long-run economic growth. In a Solow model without technological progress, where you only have physical capital accumulation, perpetual long-run economic growth is impossible. Now, does this change when we have the possibility of automation? To analyze this, we again use the framework that I've proposed before, and we can now pursue two different avenues. We can either assume, as in the Solow model, that there are no optimizing agents in the background, and just a share of capital is, or a share of savings is channeled towards traditional capital and the share is channeled towards automation capital. Or we can assume the presence of rational individuals. They would then allocate their savings optimally between the two savings vehicles such that arbitrage possibilities vanish and the rates of return of the two capital stocks would be the same in equilibrium. Which way we pursue doesn't matter for the final results. They are the same, except for one constant that is between 0 and 1 in both cases, but the qualitative predictions are exactly the same. It's slightly easier to use the rational individuals, and so I will pursue this way. So we assume that there are rational investors such that the rate of return on traditional capital and the rate of return on automation capital, they equalize. And here we note that I assume that the rates of depreciation are the same for these two assets, so it just cancels out. And then we have on the left-hand side the rate of return, or in this case also the interest rate with respect to traditional physical capital, and on the right-hand side the interest rate with respect to automation capital, and they would equalize. Then we see already that a lot cancels out here and simplifies. So if we carry out all these simplifying steps, we can express the automation capital stock in the economy as a function of the traditional capital stock and the number of workers. And it's clear here that if the traditional capital stock increases, so does the stock of automation capital. But if the number of workers increases, the stock of automation capital would decrease in equilibrium. And both make sense. If you have more physical capital, that means you have more assembly lines. You would need to staff them. And one way to staff them is by using industrial robots. Another way to staff them is by using workers. So if you have more workers, you don't need as many industrial robots. So the number of workers reduces P. Now we can plug in P into the production function, and if we simplify, we get output as a function of traditional physical capital with here a coefficient, but we see that there is no exponent of physical capital anymore. So the exponent is 1, which means that the marginal product of capital does not diminish anymore. That means, in turn, that long-run economic growth becomes possible even without technological progress, because now, as long as physical capital accumulates, we would also have an increase in GDP in the economy. So we can overcome actually the diminishing marginal product of capital by using industrial robots. And that's now again clear and consistent with the narrative that we had before. We can produce without the use of labor. We can think about an assembly line that is solely staffed by industrial robots. So physical capital basically can produce on its own. One's in the form of traditional capital, the assembly line, and the other is automation capital that works on the assembly line. You don't need any workers anymore, and therefore the diminishing marginal product that you would have with traditional physical capital is gone away, because you can use the other capital actually to work on the assembly line. So long-run economic growth becomes possible because the accumulation of robots prevents the marginal product of traditional capital from falling. Now we also show this formally. First we compute output per capita. That's just GDP here divided by the number of workers. So if we do that and we denote by lowercase letters per capita or per worker variables, we get per capita GDP as a function of per capita traditional capital here. We also divide the expression that we had here by the number of workers and get this expression here. So we would have automation capital per worker as a function of traditional capital per worker, and here -1. And automation capital per worker is also in the literature sometimes defined as automation density. So basically the number of robots per 1,000, 10,000, 100,000 workers. And then from this expression, we can compute the change in automation density as the time derivative of P. And we see immediately, so this here is constant, this here drops out, that the change in P is associated to the change in K. Now we note that the accumulation of total capital is the accumulation of traditional physical capital plus the accumulation of automation capital, and that's equal to aggregate savings, which is the saving rate multiplied by total income in the economy. And from that, of course, we have to subtract the capital stock that depreciates at each moment, which is the share delta of K and P. Now we can use similar derivations as in case of the standard Solow model to arrive at the evolution of capital per worker and automation capital per worker, which is then equal to saving in terms of per capita. And we subtract not only the depreciated capital stocks, but also the diluted capital stocks due to population growth. I don't repeat the steps here, because you can find them in the chapters on the Solow model, but basically this is straightforward, just by the definition of K over L and P over L to compute the evolution of them if you have population growth. Then we can substitute in this expression the expressions that we derived on the previous slide. So we substitute in P dot here, so that we get on the left hand side only K dot. We substitute in for y this expression here, and then we simplify and arrive at a rather complicated expression here. But the good thing is that we can rearrange it, so we can isolate K dot on the left hand side, and we can note a few things, that the limit of 1 over K as K goes to infinity becomes equal to 0, so it drops out here if we divide by K. And 1 plus 1 minus alpha over alpha is equal to 1 over alpha. If we carry out all these steps and simplifications in this equation, we finally arrive at the growth rate of traditional capital per worker as a function of the saving rate, the elasticity of output with respect to traditional capital, alpha to the power of alpha, 1 minus alpha to the power of 1 minus alpha, the rate of depreciation, and the rate of population growth. Now, in the standard Solow model, we would have that in this expression here, the capital stock shows up with a negative exponent. And that would always mean that as capital accumulates, the capital rental rate decreases, and at some point, this expression here would not be higher than the rate of depreciation plus the rate of capital dilution anymore. And at this point, the steady state, capital accumulation stops, the economy per worker, and the economy starts to stagnate. And from there on, there is no growth possible without technological progress. Now here, this mechanism is not at play anymore, because it was offset actually by the use of a second capital stock, automation capital. What we see here is that this term here is always constant, and for certain parameter values it will be higher than the rate of depreciation plus the rate of population growth. In this case, you would have perpetual growth in capital per worker. Now we see from these expressions that we had before that if we have perpetual growth of capital per worker, we also have perpetual growth of automation capital per worker and of per capita GDP. So we can show actually in this model that the long-run growth rate of automation capital per worker, of per capita GDP, and of the traditional capital stock is equal to the expression that we had before. So if this is positive, we have positive perpetual growth in the economy, irrespective of the fact that we do not have technological progress. And this is a consequence of automation capital overcoming the diminishing marginal product of traditional physical capital. Now what we also see is that the growth rate of the economy increases with the saving rate or the investment rate, which is the same in a closed economy then, and it decreases with the rate of depreciation and with population growth. And actually this is very much in line with empirical evidence. We know that the long-run economic growth rate actually decreases with the population growth rate across countries, and it increases with the gross investment rate. So it's more in line with empirical evidence and say some semi-endogenous growth models that predict a positive association between the population growth rate and the economic growth rate, at least across countries. Had we instead chosen to abstract from rational investors and just assume the standard Solow model without optimizing agents, then we would have assumed that a share of total savings is channeled towards traditional physical capital, this share being equal to SK and of course in between 0 and 1. Then the result would have been this growth rate here, which if we compare it to this growth rate here, is basically the same, except for the fact that SK to the power of alpha here and 1 minus SK to the power of 1 minus alpha here, they would be alpha to the power of alpha and 1 minus alpha to the power of 1 minus alpha here. But since alpha is in between 0 and 1 and SK is between 0 and 1, nothing actually changes. Finally, a comment: if the saving rate is comparatively low, it could be that this expression here is low as well, and then a stagnation steady state would be obtained, as it is basically known we would not have perpetual growth in such a model. Now we turn to the issue of wage inequality, and here we know that the Solow model is silent on this issue. The reason is that there are no different types of workers in the standard Solow model, and therefore wage inequality cannot be analyzed. We now extend the Solow model by two types of workers, skilled workers and unskilled workers, and we again have robots, automation capital, that is a perfect substitute for unskilled workers. So the unskilled workers can be thought of as the assembly line workers that are substituted by industrial robots. Now we have a CES structure in the labor part of the model. Outside of the CES structure, we have traditional physical capital again with an output elasticity of alpha, so we have a Cobb-Douglas structure here, but inside the labor part we have this CES structure where gamma determines the elasticity of substitution between unskilled and skilled workers. If gamma goes to minus infinity, unskilled and skilled workers would be perfect complements. For gamma approaching 0, we would have a Cobb-Douglas representation here as well, and for gamma going to 1, we would have perfect substitutability between unskilled and skilled workers. Now we definitely have perfect substitutability between robots and unskilled workers, and the substitutability between robots and skilled workers is determined by the substitutability of unskilled workers and skilled workers. So gamma at the same time determines the elasticity of substitution between unskilled workers and skilled workers and between robots and skilled workers. Now we can compute the wages of skilled workers and unskilled workers, in this case again as the marginal product of the corresponding production factor. So if we want to have the skilled wage, we take the derivative of this production function with respect to LS. It's a rather long expression here that is already a little bit simplified. And we do the same if we want to know the wages of unskilled workers, but then take the derivative with respect to LU and get this expression here. Now, if we want to know the skill premium or the difference in wages between skilled and unskilled workers, we can just divide WS by WU and get this skill premium, or the ratio of the skilled wages to unskilled wages. And we see here already a lot of stuff drops out because we have Y here that drops out, 1 minus alpha drops out. We have this expression in the denominator being the same and drops out, and only a comparatively short expression remains that depends in particular on automation capital. Now what we see is that as long as gamma is not equal to 1, which would mean that skilled and unskilled workers are perfect substitutes, but then the whole thing would be meaningless because we wouldn't have to introduce these types of workers when they are perfect substitutes anyway. And unless this is the case, we see that accumulation of automation capital increases the skill premium. So the ratio of wages of skilled workers to unskilled workers increases when there is more automation capital in the economy. So the Solow model with skilled and unskilled workers and automation predicts an increase in the skill premium over time as automation capital accumulates, and this is again consistent with the experience since the 1980s. We can show this by plotting the skill premium in the United States here as a dashed line from the 1970s to 2015, which has increased from about 70% to now about 120% in 2015. And the solid line is the model prediction for the observed increase in automation capital that we've seen. And we see that the model predictions are quite consistent with the stylized fact for the skill premium as we observe it in the data. So now we can summarize how the model predictions of the standard Solow model change once we augment the model with automation capital in the form of industrial robots. And here the model predicts that perpetual growth becomes possible because we have automation capital that we can use instead of workers, and so overcome the decreasing marginal product of traditional physical capital, basically. This is more kind of a theoretical possibility, but from an empirical perspective, the two other points are more important, namely that the model predicts a decreasing labor income share from the 1980s onwards, so once automation capital becomes widely available, and this is consistent with the stylized facts that we observe since the 1980s. In addition, an extension of the model with unskilled and skilled workers, and with automation capital that substitutes for unskilled workers, we get the prediction that the skill premium increases with automation, and also this takes place since the 1980s, so the model can also explain the increase in the skill premium since the 1980s with the accumulation of automation capital or the use of industrial robots.